Okay, so, there's just so much information out there. It feels almost impossible sometimes to really stay on top of things, to really get what's going on. And that's basically why we do the deep dive. We try to, well, cut through all that noise, dig into the research, and give you the core insights you need on complex stuff fast today. We're jumping headfirst into cryptographic innovation. Really fascinating area. We're looking at something called Verifiable Random Functions, VRFs, and specifically how some pretty groundbreaking new work is making them way more efficient and also more secure. So our mission today is to unpack this research paper. It's called MUSEN, Aggregatable Key Evolving Verifiable Random Functions and Applications, and some related publications too. We'll pull out the key ideas and show you why this, well, it sounds technical, but why it actually matters for systems you probably use, especially blockchains.
Yeah, and it's important to stress this isn't just, academic theory locked away somewhere. These concepts, they're fundamental. They're the building blocks, really, for security and efficiency in decentralized tech and advanced crypto protocols. This stuff is foundational.
All right, let's unpack this then, starting right at the beginning. What exactly is a verifiable random function, a VRF? So imagine it like this. Someone has a secret key. Yay. And they can use it to generate a number that seems random, pseudo-random. But here's the kicker, the really crucial part. It also spits out a proof, a mathematical proof.
Exactly.
And this proof shows that the number is valid, and literally anyone can check it just using the corresponding public key.
That's the key, verifiability. It's not just randomness. It's randomness you can prove was generated correctly according to the rules without revealing the secret key itself.
So you're publicly demonstrating, hey, I generated this random value, and here's the proof. Like a lottery draw you can audit.
Precisely. And they're already used quite a bit. A big one is in choosing participants, like committees in crypto protocols. Think proof-of-stake blockchains, for example. VRFs are often used there to select who gets to propose the next block. It's like a secure, verifiable lottery for leadership. Cardano uses this kind of approach.
Right.
Or for picking smaller groups, these committees for things like multi-party computation, MPC, especially in models like YoS, where you need anonymous groups chosen in a demonstrably random way.
Right, so verifiable randomness is already pretty important now. This new research, it adds two big improvements.
Yeah.
Let's talk about the first one, the key evolving property,
Yeah.
i.e., what's the problem this solves? Like, imagine your secret VRF key gets compromised, maybe years from now. Could someone use that old key to fake outputs from the past?
Yeah.
Kind of rewrite history?
Yeah, that's exactly the threat. And it's a serious one. What's really fascinating, technically elegant even, is how the KE property tackles this head-on. It's specifically designed to stop an adversary, even one who successfully corrupts someone and gets their secret key, from being able to forge proofs for VRF evaluations that happened before the key was compromised.
Ah, okay.
And this is super critical for systems that run for a long time, like blockchains, right? Parties are involved for potentially years. Keys might get exposed or, people might just stop protecting old keys properly. This happens in nothing at stake type situations.
So how does it work? How does this key evolving thing actually protect the past?
It's pretty neat. Essentially, you assign a specific version of the signing key to each time period or slot. To generate the key for the next slot, the signer evolves their current key, but the public key, that stays the same, totally static.
Okay.
And here's the crucial step. Once a time slot is over, the signer securely erases the key version for that slot. Gone. This gives you forward security. Even if someone steals your current key, they can't go back and forge things for past slots because those keys simply don't exist anymore. They've been securely deleted.
Like shredding yesterday's documents. Clever. Okay, so that's key evolving. What's the second big improvement? Aggregation. You mentioned lots of VRFs might be needed, maybe under different keys, leading to lots of proofs. Sounds bulky.
Exactly. That's the challenge aggregation solves. Imagine a large system needing hundreds or thousands of these verifiable random outputs, each potentially with its own proof. That's a lot of data.
Yeah, I can see that being a problem.
Aggregation is this amazing ability to take proofs for multiple VRF evaluations and get this, even if they're for different inputs, under totally different secret keys and combine them all.
Into what?
Into a single, small, constant-size proof.
Wow, okay, so instead of a whole stack of proofs, just one tiny one that covers everything.
That's the idea. It's a massive win for efficiency. Think about bandwidth, storage space on the blockchain. It shrinks everything down dramatically.
Right. Okay, this is where it gets really interesting then. Because the big contribution of this paper, the MUS paper, is putting these two things together, right?
Yeah.
The aggregatable and key evolving VRF. The AKE-VRF.
Precisely. That's the breakthrough. Because while, cryptographers had tools like key-valving signatures or separately things like aggregated signatures.
Right, the pieces existed.
Pieces existed, yeah. But getting a VRF construction that gave you both the aggregation efficiency and the forward security from key evolving, plus, crucially, the specific randomness properties VRFs need, like pseudo-randomness and unbiasability that hadn't been done before. This work really fills that gap. It delivers the whole package: aggregation, forward security, and verifiable randomness all in one primitive.
And who came up with this? It sounds like a big effort.
It was, yeah. A collaboration between researchers from several institutions. Tokyo Institute of Technology, which is now Institute of Science, Tokyo, Monash University, and the IT University of Copenhagen. Yeah, really strong group. And the work, as you mentioned, was presented at the SCN conference in 2024. You can find the paper itself on the IACR ePrint archive. That's the main public archive for crypto research, and also mirrored on the IIG library website.
Okay, good to know where people can dig deeper. So we've got the tech, AKE-VRFs, aggregation forward security. Cool stuff. But, the big question is always, so what? What does this actually mean for real-world systems? You mentioned blockchains.
Absolutely. Let's talk proof-of-stake blockchains. One of the perennial concerns in any blockchain, POS or proof of work, is block size.
Right. How much data fits in each block.
Exactly. And any extra space you can free up in those blocks is incredibly valuable. It affects how many transactions you can process, how fast the network is, how much data nodes have to store long-term.
Makes sense. Less data, faster network,
Yeah.
Easier for people to run nodes, potentially more decentralized.
You got it. And AKE-VRFs directly impact this. They allow for significantly smaller block headers.
The header is like the summary information for the block.
Yeah, metadata about the block, including proofs needed for validation. So take a well-known protocol like Ouroboros-Prous. Its standard proofs take up a certain amount of space, measured in bits. But using the MUSEN design, based on these AKE-VRFs, you can drastically cut that size. The paper gives specific numbers, showing a really significant reduction.
How? Why is it smaller?
Because one single compact AKE-VRF proof can now be used to derive multiple random outputs that the protocol needs. For instance, the randomness needed to choose the next block leader and the randomness for something called a random beacon, they can both come from the same aggregated key evolving proof. You don't need separate proofs anymore.
Okay. One proof, multiple uses. Very efficient.
Very. And they even propose a heuristic MUSEN version that goes further.
Heuristic meaning?
Meaning it relies on slightly stronger assumptions, perhaps not fully proven in the standard models yet, but likely secure in practice. And this heuristic version aggregates basically everything needed into one proof. It gets the block header incredibly small.
But there's a trade-off with that one, right? Something about bias.
Yeah, that's the nuance. The paper points out that this super aggregated heuristic MUSEN design might introduce a slightly larger potential for bias in leader selection.
Meaning a bad actor might have a tiny bit more influence over the randomness.
Potentially, yeah. If they get lucky and have multiple valid blocks they could propose, they might be slightly more able to choose one that benefits them. It means you might need to be a bit more conservative with security parameters to compensate. It's flagged as an area needing more research to fully quantify that risk.
Interesting. So efficiency versus maybe a tiny bit more potential risk. A classic crypto trade-off.
It often is, yes.
And there was another optimization mentioned, something about Merkle trees.
Ah, yes, for the public keys in POS. Instead of listing potentially many public keys, you can use a Merkle tree. You just need to store the small root hash of the tree, which represents all the keys. It makes managing and verifying large sets of public keys much, much more efficient. AKE-VRFs work nicely with this.
Cool. Okay, so proof of stake gets a boost. What about POPOS? Proofs of proof of stake.
Right, POPOS. Think of these as ways to create efficient sidechains or super light clients.
Sidechains being like parallel blockchains. And super light clients for, say, mobile phones to check the chain.
Exactly. POPOS lets you compactly prove the state or history of a PS chain. AKE-VRFs improve these too. They allow for aggregation of signatures and proofs within the data structures used in POPOS, these things called handover trees that track committees over time. So again, it leads to smaller proofs, making these light clients and sidechains more practical and efficient.
Okay, this is powerful stuff for blockchains.
Yeah.
But you hinted at even more. Sort of. Futuristic applications. Encryption to the future. Authentication from the past. Sounds wild. Let's start with ETF, encryption to the future. What's that about? Sending messages to people who haven't even been chosen yet?
Pretty much. It's a cryptographic primitive that lets you encrypt a message intended for a party who will be randomly selected for some role at a future time. You send it out now, addressed to whoever wins the lottery for slot X.
Wow. Okay. And where would you use that?
A key example is this framework called YOFO, You Only Speak Once. It's for multi-party computation where committees are chosen anonymously and need secure communication channels set up before they even know who they are. ETF enables that.
And authentication from the past, AFP,
Right.
the counterpart.
Right. AFP lets a party, after they've been selected for a role in slot X, prove that a message they're sending now genuinely originates from their execution of that role back in slot X, authenticating past actions.
Okay, fascinating concepts. But what was the problem with older ways of doing this?
Well, there was a pretty significant issue, a grave issue, as the researchers sometimes call it. With previous EAT-FFP schemes, if a participant's long-term secret key was compromised at any point in time, an adversary could potentially go back and decrypt all past messages ever sent to that participant via ETF. And they could also forge AFP authentications, essentially signing messages as if they were that participant acting in a past role.
Yikes. So one key compromise could unravel past privacy and authenticity.
Completely.
Yeah.
A total break of forward security.
And AKE-VRFs fix this. How?
They provide exactly the missing piece, forward security. They achieve this using what they term a witness-evolving lottery predicate.
Okay.
Basically, the VRF secret key itself acts as the witness for the lottery that selects the participant. And because it's a key-evolving VRF key, it gets evolved and the old version securely erased after each time slot.
So the key used to decrypt messages or authenticate for slot X is destroyed after slot X.
Precisely. So even if an attacker compromises the key for slot Y, they can't use it to decrypt ETF messages sent to slot X, nor can they forge AFP authentications for slot X. The past remains secure.
That is genuinely elegant, using the VRF's own key-evolving nature to secure these advanced primitives.
It really ties everything together nicely.
Okay, so let's try and wrap this up, pull the threads together. What are the big takeaways from this deep dive into AKE VRFs?
Yeah.
That seems like a really significant step forward in cryptography, right? Combining aggregation and key evolving in one VRF wasn't trivial.
Definitely a leap. It solves real, practical problems in efficiency and security, especially for foundational tech, like proof-of-stake blockchains.
Yeah, we saw the impact. Smaller block sizes, potentially faster transactions, better scalability, and crucially, that robust forward security, protecting against past compromises.
Absolutely. And if you zoom out a bit, this kind of innovation shows how these fundamental crypto tools are constantly being improved, combined in new ways, really pushed to meet the demands of increasingly complex, decentralized systems and these, future-looking protocols like ETF and AFP. It's an ongoing evolution.
Building better tools for a more secure and efficient digital future.
That's the goal.
So here's a final thought for you, the listener, to chew on. We talked about that heuristic MUSEN design, maximum efficiency, super smart proofs for blockchains, but maybe that tiny potential increase in adversarial bias. Given these kinds of trade-offs, which pop up all the time in cryptography and system design, how do you think designers should balance these things? Is maximum efficiency the ultimate goal, even with a slight, perhaps theoretical, increase in risk? Or should they always prioritize minimizing bias, even if it means slightly less optimal performance? Where do you draw the line? Something to think about.